Okay, trends in the periodic table. Here we go. Complete the sentence. In their periodic tables, Newlands and Mendeleev arranged the elements in order of what? Well, they arranged them in order of atomic mass. You've just got to remember that. That's what those guys did. They arranged the elements in order of atomic mass. Okay. Name the particle that allowed the elements to be arranged in order of their atomic number in the modern periodic table. Well, it's the proton, okay? It's the number of protons that defines an element as that element. Lithium is only lithium because it has 3 protons, okay? Fluorine is fluorine because it has 9 protons. So elements are defined by their number of protons. Okay. Which one of the 9 elements shown has the lowest boiling point? Right. So we have to draw on our knowledge of boiling points in the periodic table to answer this question. So let's cover that first and then we'll actually answer the question. Right. To remember boiling points in the periodic table, draw a couple of arrows like so. Okay. In group 1, the alkali metals, draw an arrow going up. Okay. In group 7, the halogens, draw an arrow going down. Okay, this is melting points and boiling points. In group 1, as you move up the group, the melting points and boiling points of these elements increases. And it's the opposite for the halogens. As you move down the group, the melting and boiling points increases. Okay? Now, what about the rest of the periodic table? Well, for the transition metals, this pink block, they generally have high melting and boiling points, okay? But you can kind of work that out. I mean, copper is there, and you know that copper must have a pretty high melting and boiling points because it's what the pipes in your house are made of. You send boiling water through it, so it must be at least 100 degrees C. And imagine trying to heat copper to melt it. You're going to need a lot of heat, right? So the transition metals, generally high melting and boiling points. Right, so what about this block here? Well, for your age group, this sort of level, age 14 to 16, let's ignore this bunch there. Don't worry about them. Not relevant. You don't need to know. And let's also put a line there. Okay? These 4, kind of group them in with the transition metals. They have high melting and boiling points. Okay, so I'll write this in. So transition metals in pink, high melting points and boiling points generally, and same for these 4 here, high melting point and boiling point. Okay, and the rest low melting points and boiling points. Okay, so this lot here, everything else, in other words, low melting point and boiling point. Okay, and that is more than enough that you need to remember for this sort of level. Okay, so to sum up, draw an arrow up in group 1, down in group 7, melting points and boiling points increase in that direction, an increase going down in that group, high in this block, high in that bunch of 4, and low for everything else, generally. Okay. And the final thing to say actually is that if you have to ask yourself, does fluorine or rubidium have the lower melting point? Well, it's fluorine, okay? these guys melt and boil more easily than these guys. Okay? So that is now the full picture. So we can answer the question. And the question was, which one of the 9 elements shown has the lowest boiling point? Okay, well, we know it's not copper because these have a high melting and boiling points. So we know from these arrows it's either fluorine or rubidium, and I just told you that these guys melt and boil more easily than these guys. So the winner is fluorine. Okay, let's move on. Copper and potassium have different melting points and boiling points. Give one other difference between the properties of copper and potassium. Okay. Actually, before I answer that, I'm just going to write in a couple of elements. Let's put in... It's good to remember what goes here. Okay, that's carbon, and this is silicon. So the line of where the melting and boiling point suddenly changes is just to the right of carbon and silicon. Okay, carbon and silicon both have very high melting and boiling points of the order of thousands of degrees centigrade or Kelvin. And then it suddenly falls here, and nitrogen there has very low melting and boiling point. Okay, right, so where were we? Copper and potassium have different melting points and boiling points. Give one other difference between the properties of copper and potassium. Right, so we're now looking at copper and potassium, K there. So one other difference between the properties of copper and potassium. Right, to answer this question, or to answer it best, you need to draw on your knowledge of how reactivity varies or trends in the periodic table. So let's draw that in. Let's use pink. So with reactivity, we're going to draw 2 arrows again, but they're the exact opposite of melting points. Okay, so this time, this arrow through group 1 is going to go down, and the arrow in group 7 is going to go up, right? So pink arrows is reactivity. So what that means is that reactivity increases as you move down group 1. And reactivity increases as you move up group 7. Or, put it another way, reactivity decreases as you move up group 1. And reactivity decreases as you move down group 7. So, to actually answer the question, give one other difference between the properties of copper and potassium. Well, the best answer is to say that potassium is more reactive than copper. Again, getting back to the fact that the pipes in your house are made of copper, it must be unreactive. Otherwise, it would react with the water flowing through it and you'd poison yourself or something. Okay? So you can use that to remember that copper is pretty unreactive. Whereas potassium, maybe your teacher's thrown some sodium in some water or even some potassium. You see what happens. It reacts vigorously. Okay? So you know that potassium must be pretty reactive. So therefore, potassium is definitely more reactive than copper. And that's the best answer for this question. Okay, I've made a note. You could also say that copper is a metal and it's therefore harder than potassium. True, you probably get the mark, but it's better to talk about reactivity, I think. To remember that copper is harder, well, firstly, copper is a metal. You know, metals are pretty hard generally, but have you seen your teacher pull out some sodium in class? Sodium's kept in oil to stop it reacting with the oxygen in the air. So it's going to be have similar properties to potassium, right? Because that's why they're in the same group in the first place. Groups have similar properties. And you know that if you've seen your teacher pull the sodium out of the oil and you can slice it with a knife, it's pretty soft. It's a solid, but it's a soft solid. So much softer than copper. Okay, let's move on. Explain why the reactivity of the elements increases going down group 1, okay, from lithium to rubidium, but decreases going down group 7 from fluorine to iodine. Okay, so I've told you what the reactivity pattern is, now we've got to explain it. And this is 4 marks. So this is textbook answer, okay, common exam question. So to get 4 marks out of this, for both group 1 and group 7, okay, as you move down the group, the atoms get larger, right? So as I'm going to do this in shorthand, but you have to write it out in full, obviously. As you move down the group, atoms get bigger. Okay? And therefore, the outer shell electrons get further from the nucleus. Okay? So iodine, okay, is a much larger atom than fluorine. Fluorine's relatively small and they get bigger as they go down. Same here, as you go down, rubidium is a bigger atom than lithium. Okay? So, therefore, there's a less electrostatic attraction to the nucleus. Well, no, just less electrostatic attraction between the outer shell electrons and the nucleus. Okay? And also, you can say, therefore, as you move down the group, there's more shielding. What that means is there are more electrons on the inner shells in between the nucleus and the outer shell electron, and that's called shielding. Okay? So that's true of both group 1 and group 7. Okay? As you move down both groups, all these things are true. Now, and this is where we split off between group 1 and group 7. So for group 1, all these things mean that as you move down the group, it's easier to remove the outer shell electron, and that means it's more reactive. So as you move down the group, it's easier to remove the outer shell electron. Okay? Because of all these reasons we've listed. And it's the opposite for the halogens. Okay? Group 7, as you move down the group, it's harder to gain, okay, an outer shell electron. And that will get you full marks. Okay? That's the full picture. To explain what the reasons for this, Group 1, when they react, they lose their one outer shell electron. That's what makes them reactive, okay? Lithium, when it loses its electron, it becomes lithium plus. Sodium, when it loses its electron, it becomes sodium plus. One electron has a -1 charge. So if sodium has lost that outer shell electron, one negative charge is gone, so it becomes +1. Okay? And therefore, the easier it is to remove that outer shell electron, the more reactive the element is. For the halogens, okay, when they react, they gain one electron. Okay? So fluorine would become F-, it's gained an electron with a -1 charge. Chlorine becomes chlorine minus. That's called fluoride and chloride. Ide meaning it's got that extra electron. It's an ion. So they react by gaining an electron. And therefore, as you move down the group, for these reasons, the harder it is for that element to gain an electron. In other words, the harder it is for it to react, and so the less reactive it is. Okay, and that will get you your full marks. So remember that for your exam. And incidentally, this is why Group 1 and Group 7 go so well together. Group 1 really want to lose one electron, so they have a full outer shell. The next shell down, what's left is now full. It has the so-called noble gas electronic configuration. And the same with the halogens. The reason they want to gain one electron is so they have the noble gas electronic configuration. So if these guys really want to lose one electron and these guys really want to gain one, they're a good match. So you often see things like sodium chloride. Overall, no charge, but the chlorine has taken an electron from the sodium. You could have any matchup. You could have sodium fluoride, okay, NaF. You could have lithium bromide, okay, and so on. All right, there you go. That's trends in the periodic table.